All right, so here we go. We've got the Laplace equation in polar coordinates right here in the blue. We've got our domain here. Slight notational change. I've been calling the radius of the domain R0 before, R naught. I'm going to call it A here, just to make it a little bit easier notationally down the road. So we've got our domain here, and we want to now try to solve this equation. And the last thing I have to do is define some boundary condition. So I've got the boundary of D here, and on this boundary here, I'm going to define my U of, so it's U of R theta in general, so U of when R is equal to A and theta, it's going to be some F of theta. I don't want to specify it as an example. I would just leave it as some F of theta. However, this F of theta, it can't be just anything. This has to be periodic with period 2 pi. All right, so the things match up on the boundary. Furthermore, if I look at kind of the whole problem here, I also need my solution U of R theta to be periodic in theta with period 2 pi. Okay, in order to make sense, basically wrapping around right here, wrapping around 0 equaling 2 pi. It's got to map on. There's another little condition that I'm going to impose that just basically makes sense, and we're gonna see why we need this a little bit later on. But I'm going to make a little comment. I also need my U, my solution, to be bounded. All right, so can't have things go into infinity, basically, on this domain. Makes sense with the physical manifestation of Laplace's equation. Okay. What do I do to solve? Let me think of all the methods I have. Oh, I've only got one. It's separation of variables, so let's see if that works. Separation of variables. Let's see what happens. That is, I'm going to let U of R and theta equal some, usually we say xy or x and t. Now we'll say R and theta. So capital R of R, and then capital theta. I mean, I know there's little things in there, forget that, of theta. I'll just use a big one and a little one. Okay, well, plug into the PDE. See what we get. All right, well, I get a second derivative with respect to R, so that becomes an R double prime times theta. And then I have a plus 1 over R, U sub R, which becomes R prime theta. And then I have 1 over R squared, U sub theta theta, which becomes R theta double prime. And that equals 0. I'm going to do my usual division by R theta. And I'm also going to multiply the whole thing by R squared. Okay? And that's going to give me R squared, R double prime over R, plus R prime over R, equals negative theta double prime over theta. And of course, I've got my usual game here. Blah, 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 blah. Function of R only, this thing. Function of theta only, so goodness gracious, it must equal some arbitrary constant lambda. Again, you can make that positive or negative lambda. I'm going to make a positive lambda for ease in setting this problem up. All right, so we're back to ODEs. So we obtain the two ODEs that look like R squared, R double prime, plus R prime, minus lambda r. So I've multiplied that all through by r. It drops onto the lambda up here. So this r comes up, gets onto the lambda. So there's my first ODE in r. And then I've got the theta one, that's theta double prime. It's going to be a plus lambda theta equals 0. And then the boundary conditions, they're going to be periodic in theta. All right, so let's take this one on. Let's grab U. This one's not so bad. Looks like our usual problem. We've been here lots before. Theta double prime plus lambda theta equals 0. And we've got the periodic boundary conditions, and I'm going to make it periodic at 0 and 2 pi. That's where I'm going to match the boundary. That is theta of 0 is equal to theta at 2 pi. And then similarly, we're going to make it smooth across there. So theta prime at 0 is theta prime at 2 pi. And, well, check lambda less than 0, lambda equals 0, lambda greater than 0. Lambda less than 0. What do we get? Okay, we'll let lambda equal the negative beta squared in this case. So my theta comes out, you remember this, it's cosh and sinh. All right, so A cosh beta theta plus B sinh beta theta. If we apply theta of 0, cosh of 0 is 1, sinh of 0 is 0, so you get A. If I plug in 2 pi there, I get A cosh beta 2 pi plus B sinh beta 2 pi. 2 pi beta. You take the derivative, you plug in the same conditions. So I need theta prime is equal to beta A sinh beta theta plus beta B cosh beta theta. You plug in 0. Theta prime is 0. The sinh goes away and the cosh goes to 1. So you get a beta B. Theta prime of 2 pi is equal to beta A sinh 2 pi beta plus beta B cosh 2 pi beta. 2 pi beta really looks a lot nicer than beta 2 pi. This is bothering me up here. All right, so you get off. You get off. 2 pi beta. 2 pi beta. All right, divide the whole thing by beta here and set that equal, and you basically get A sinh 2 pi beta plus B cosh 2 pi beta equals B. Okay, so I've equated these two things together, divided the whole thing by beta. You get that equation. And then if I equate these two, you get another equation. A cosh 2 pi beta plus B sinh 2 pi beta is equal to A. And we're looking for a solution here, a non-trivial solution. The trick is to add and subtract these two equations to obtain two new equations. And if you do that, after some cancellation, there's A plus B's and A minus B's that can get divided out, but what you end up with is a statement to the effect of cosh 2 pi beta plus sinh 2 pi beta is equal to 1, and then you get cosh 2 pi beta minus sinh 2 pi beta. That's from the subtraction of the two equations. is also equal to 1. And yeah, basically if you let beta not equal 0, you get no solution. Okay, except A equals B, both equaling 0, if beta is not equal to 0. All right, so trivial. Nothing out of here. Okay. What do we got up next? Lambda equals 0. My theta solution is A plus B theta, little theta. Okay. Theta of 0 is equal to A equals theta of 2 pi, which is A plus B times 2 pi. All right, so that means that A equals A plus 2 pi B. And, well, last I checked, probably means B equals 0. That's the way that one works. And in the derivative, theta prime is equal to B. So theta prime of 0 equaling theta prime at 2 pi. Well, what, B equals B. Yeah, that works. No restriction then on A. So I do, in fact, although B equals 0, so I guess that's, I mean, there's nothing to be talking about in this line right here. That's all just 0 equals 0. But anyway, you do get A as free. So that means we do get a non-trivial solution here. For lambda equals 0, we have the eigenfunction 1. Okay, theta equals 1. All right, then normally at this point I would do lambda positive, but I actually want to go over and look at the R equation, the capital R equation, just to see what this is going to suggest for lambda equals 0. So let's look at the R equation for this eigenvalue, lambda equals 0. All right, so back to the ODE, we'll get R squared, R double prime, plus R prime, and then the lambda R term is just 0. So I end up just getting 0 here. All right, so it's an ODE. There's should be maybe a slightly familiar structure to this thing. Okay, specifically, I want you to think about the R squared, and then the second derivative of the unknown function, and then the R, the first derivative of the unknown function, and then often there's another piece there. That piece just happens to be 0. This is called an Euler equation. It's one of the few variable coefficient ODEs that we can solve in kind of closed form without doing anything special to it. So we would have looked at that in ODEs. If you recall the Euler equation, we look at the roots. Right, now the generic form of an Euler equation, we might look at it something, I'll keep it in R, so R squared capital R double prime. We would say there's some alpha R capital R prime, and I'll use gamma here. So gamma R equals 0. This gives the associated characteristic equation. I'll use S, so S minus 1 plus alpha S plus gamma equals 0. And so in the case up here, we have alpha equals 1 and gamma equals 0. All right, so I look at this equation, this capital F of S, which is S minus 1 plus alpha S, so that's plus S, plus gamma, which is 0. And I want the roots of this thing. S squared minus S plus S is just S squared equals 0. S equals 0 twice, in some sense. So these are real, repeated, or equal roots. And if you recall, you probably don't, but it doesn't matter because I do. I recall that this gives you the solution form, let's call it C plus D ln R, R to the S. Okay, now we just determined in this case that S equals 0, so you just get R to the 0 or 1. And so R is equal to C plus D ln R. I find this thing slightly problematic. Okay, think of our domain. Our domain goes out to some a value and then starts at R equals 0 on the center of the domain. And I wanted my solution U bounded on the domain. But ln R, unfortunately, goes to minus infinity as R goes towards 0. So I don't like that term. That solution is not bounded. And so what that implies is that D equals 0 in order to maintain a solution U that is bounded. And so this boils down to just R equals, well, C, but generally speaking it's 1. We'll multiply by an arbitrary constant in the superposition of all my solutions down the road. So for lambda equals 0, I basically got theta equals 1 and R equals 1. So I'm going to call this as the start of my set of solutions. Sorry. There. R0, theta 0 is just 1. Okay, i.e. U sub 0 of R and theta. The very first term is 1. All right. I'm free to move on. Let's do lambda positive. We all know the solution. I'm letting lambda equal beta squared here, so a cos beta x plus b sine beta x. All right, and then we want theta periodic. Theta is periodic period 2 pi. I mean, look, they're cosines and sines. So if beta equals n as 1, 2, 3, and so on. Okay, of course we need lambda positive, so that rules out n equals 0. All right, so that's pretty easy. Got those. Let's go over to the R equation. Okay, so basically I have integer values for beta. Okay, now the R equation involves a lambda, that's the beta squared. So in our case I have R squared, R double prime plus R prime. And then I have a minus beta squared, R equals 0. And again, this gamma is equal to the minus beta squared in my Euler equation. Alpha is equal to 1 again. I go to the characteristic equation, this capital F of S, to figure out my roots of this thing. S minus 1 plus alpha S plus gamma equals 0. There's your basic setup. Here I have S minus 1. Alpha is 1, so I just get plus S. And then I get a minus beta squared equal to 0. All right, S squared minus S plus S is just S squared minus beta squared equals 0. Oh, look at that. S is equal to plus or minus beta. Real, distinct roots of the characteristic equation for the Euler equation, the special type of ODE with variable coefficients. All right, so if you recall, these are our power functions. These are the solutions that come out. So this capital R is equal to, let's call it a constant K1. r to the beta plus k2 r to the negative beta. And we said beta was equal to n in this case, so I can write this as k1 r to the n plus k2 r to the minus n equals 1, 2, 3, all the way up. Huh, look at this fella. R to the minus n, that's 1 over r to the n. Okay. Also, as r goes to 0, you have 1 over something getting vanishingly small. That gets extremely large, becomes unbounded. Don't want that to happen in my solution. So I make k2 equal 0. And that means that the nth solution of my set of r solutions in the separation is just r to the n. All right. Now, I can formulate the set of solutions that comes out of this class of eigenvalues. And so now I'm going to write a little bit bigger here. So here we go, u sub n of r theta. I'm going to introduce these constants now, the an. I have an r times theta, and the r is little r to the n. Cos beta theta, and beta is equal to n, so that's cos n theta. And I have some bn r to the n sine n theta. All right, so again, I've combined the theta form here where I said beta is equal to n, threw that in there, and multiplied the r and the theta together, and I get this set of solutions, n equals 1, 2, all the way up. And finally, u of r theta is the superposition of all of my solutions. It's the sum of all of these solutions I've found. There's the constant one you remember that came out, and again I'm going to label this in a particular way in order for the coefficients to be consistent. I'll call it a0 over 2, so introducing that coefficient form there. I have the sum n equals 1 to infinity r at n, and then this an cos n theta plus bn sine n theta. All right, let's get a new page going here. All right, what do I got left to do? The boundary. Last step. I want u at a and theta when r is equal to a. Well, I want it to match f of theta. So I'm going to first plug in a into my solution form. That's a0 over 2 plus the sum n equals 1 to infinity. I just make r equal to a, so that's nothing exciting. A to the n, an cos n theta plus bn sine n theta. And that's all equal to my f of theta, that periodic boundary function f of theta. Now what I see here from these terms here is this is hinting at a full Fourier series. Both the sine and the cosine terms are appearing here. And I got a little a to the power n that I can deal with. That's no problem. It's just an extra piece of the coefficient that I can then later divide through by. So using the full Fourier series coefficients, no need to reinvent the wheel once again. I have a to the n. an is equal to 2 over 2 pi, or 1 over pi, integral minus pi to pi, f of theta cos n theta d theta. And I can go n equals 0, 1, 2, all the way up because of the way I've written a0 over 2 up there. That's consistent. And then I get a to the n, b sub n. Very similarly is 1 over pi, integral minus pi to pi f theta sine, nope, n theta, d theta, I get n equals 1, 2, and 3, and so on. Slightly problematic. I am going to note here that f of theta is defined on 0 to 2 pi. Make 0 to 2 pi, let's say. Not negative pi to pi. Is that a problem? No. We just periodically extend f of theta. And furthermore, cos of n pi and sine of n pi are 2 pi periodic. And if everything then is 2 pi periodic, it doesn't really matter if I integrate from minus pi to pi or 0 to 2 pi. If I have some phi in general that's periodic with period p, then the integral from a to a plus p of phi d theta is independent of a. Doesn't matter where I start, as long as I cover one of the periods, it's all good. Okay? And so that means I can just take those terms up there and I can get a formula for an and bn. I'm going to divide through by that a to the n term in each of them, and then I get 1 over pi in each of them, integral, and then I'll go 0 to 2 pi. There's no problem doing that, as stated above. F theta cos n theta d theta, f theta sine n theta d theta. Here n equals 0, 1, 2, n equals 1, 2, 3, all the way up. All right, so those are the coefficients. And we've got the full solution. Okay, given an f of theta, plug it in, crank out those coefficients, and we've got the full series solution.